How do you know if your data is lying to you? Well, it's a problem because the analyst can never know the truth, and we have to rely upon our processes to figure out what the data is able to tell us. We have to rely on statistical inference of estimation and hypothesis testing, and we have to rely on more than a single test. We have to worry about an entire testing strategy. And a need to develop that strategy is part of what this paper is about. Now, is to move past a hasty, put together regression, a hastily conceived regression, which will, of course, get us closer to the truth that we seek. Now, I am Dr. Stephen Myers, and I've been doing SAS for over 40 years, and I've taught econometrics for just about as many. And one of the things that stands out is a process of applied econometrics which is ethical data use. And I wrote a piece in Bill Frank's book here that you can see the reference to, and hope you take a look at it. It's a great reference. But there are 10 common sense rules in my article that Peter Kennedy that really talk about the kind of things that you need to watch for in order to make sure that your data isn't driving the answer and that you're following a process which will indeed give you a better answer. This is part of a larger process called the pitfalls of regression practice, which I've been working on. I want to concentrate on simply one of these today, and that is the failure to model both theory and data anomalies and to know the difference. So we're going to use an example here, and all the math and the code is in the paper on my website, and you can come back, watch this, and stop the screens to see what's going on and so forth if you want. Yeah, or you can go to a link that I will provide to you that will give you all of the code and of course the paper directly. And we're going to start out with a business problem. We're asking, what is the value of a policy change, D, some dummy variable which says we were in one state, now we're in another. We were before and after, and we want to look at an output metric. For example, tax revenue, we'll call it Y. So a modeling process in articulating the problem could be that Y has some trend over time, and we want to know if D had an effect. So we're going to model in a process that will allow that to be seen. We'll call that a structural break model here as we move forward. And the second thing is, we might say that the data stream that we observe is just some nonlinear movement of data, and that we can find a mathematical process to fully explain it. And this is something that a machine learning model might actually do. But what we want to know is whether D had an effect. Now, we need to set up the data. This is a pedagogical example. I've got 14 data points. 7 of those occurred before, 7 of those occurred after, and we need to create a number of variables. I don't have any other confounding variables in here, which the real world would suggest to you. Things like maybe local area unemployment rates or something, income levels or whatever that might have an impact upon tax revenue over and above just D. But the point I think will be well made here that it is not just the quick and hasty approach that a lot of people might come to that will get us where we want to go. So first, what we're going to do is establish the trend in the base model. And here we're just taking linear regression, and we're going to say Y is a function of the 14 time periods. We have a null hypothesis that the slope is 0, and of course when we do this, you can see the code there, we reject that mightily. The R bar square is very high, it's 0.97, and the t-value on the time trend variable is very high. So we're seeing a rise of over 3 points each year, or whatever the interval is here of time. And I show the predicted versus the actual graph there, and you can see that some residuals offline, and we'll come back to that in a minute. So what is a hasty regression? Well, it's any ill-conceived regression where you just basically throw variables in, even with the best of intentions. For instance, I have a time trend model we just looked at, and we want to know if D had an effect, so we just throw that into the model. And by throwing it into the model, we'll test it, and we'll discover whether or not D has an effect. This is hastily conceived for all kinds of reasons, and that'll be apparent as we move forward. But the graph shows exactly what that particular specification test is. It's simply a shift in the intercept with the slope or trending pattern not changing before and after. So we execute this in ProcReg, and what do we discover? D has no effect. Now, I know you, if you've done any work with regression, or many times, maybe not with a primary variable like this, but there are many times when you want to know if something has an effect, you throw in a dummy variable, it turns out to have a t-value way less than 1, and you know that eliminating a variable with a t-value less than 1 makes your regression stronger. In fact, the R-bar square for this model with D in it went down because it explains less than the model without D. So what's D? D is a useless variable, and if we were following just a hasty practice, we're done. And that would be a major mistake, as we'll see here in a minute. So why isn't hasty regression enough? A cool cartoon here, link to it if you want to see the source. And the answers from this as your machine learning system is, yeah, just pour data into a big pile of linear algebra. This is garbage in, garbage out, because we haven't given any human consideration, any practical consideration of what variables or features should be in this particular thing. So what if the answers are wrong? Well, you just keep stirring it up. You keep adding more and more, and you know, Ronald Coase, Nobel Prize winning economist, is quoted as having said, if you torture the data long enough, it will confess. So why don't we just use some automatic selection process, kind of akin to a machine learning process, certainly not the same, but ProcReg has 7 different ways in which we can actually choose these variables automatically. And what do we discover? The model that wins isn't consistent. There is not a clear pattern of a winner in this set of data that I have. Now, how do we get around this? We model the process, and we look for the data anomalies, and we try to make a difference. Most of these points you see in the block that just showed up are from the ethical process list. Use economics and common sense. Know the data generating process and the context. Clean the data, inspect the results afterwards. And most importantly, validate your specification in testing. Because in testing, it's all about rejection, not acceptance. Here's the fact that I started out with. Statisticians, analysts can never know the truth, but they have to make a decision to reject the null hypothesis or fail to reject the null hypothesis. And in this case, you can see some examples where there are some wrong decisions. They're in red. Equivalent to being in a courtroom, null hypothesis is what? You're innocent until proven guilty? No, you're innocent until your innocence is rejected by the data. And this is why we can convict the innocent and we can let the guilty go free. These are type 1, type 2 errors. What we discover in this paper is that there's another error that's very, very large, and that's called a type 3 error. And a type 3 error, according to Kennedy, is getting the right answer to the wrong question, and we're going to do that in here. Here's the real problem, is hypothesis testing is sensitive to model specification. Every single time you change the model specification, your hypothesis will change, and the results will change. So how do we get out of this conundrum? Well, first off, let's look at the residuals in that baseline regression. I showed you a graph before. Here's the graph of the residuals, and you'll see that the average residual, of course, is 0, and we have actual values scattered along that line. And I used a Loess regression, which is a nonlinear regression, just to characterize the points. And how could you avoid seeing that maybe the true model is a quadratic model? So we're going to take that on. We're going to say that one model suggested by the analysis is indeed quadratic. And because of that, D isn't necessarily in here. This is just a data path of which is the data we have tends to follow this trend path. And our hypothesis is going to be that the t-square variable that we'll add, because we're just kind of imposing a quadratic here as opposed to a linear, and we can test that out. A structural break model, on the other hand, suggests that instead of that quadratic smooth explanation of data without respect to D, what we indeed have is a model where the slope and the intercept of the linear trend before and after have changed dramatically. Again, another hypothesis. Both are suggested by this data. So what we do is we're going to test them both. And here's the SAS code for PROC-REG. We use a test statement that t-square is, the coefficient on t-square is indeed 0 versus the coefficients on D and DT are 0. And we test this and we find out that, wow, both of them have very high F values, very low P values. What did we just discover? Both models are valid. So we started out, we looked at a hasty regression, we said, hey, there's no effect whatsoever. Now we look at this, we have two different possible models, both are valid, and you can't say one's more valid than the other necessarily, although the root mean square does kind of help here. It does not by any sense validate that the other one is incorrect. Both are valid, so what do? Well, let's lay out all the models as you can see here. And these are called nested hypotheses. And what we've done in putting this test together is to compare the coefficients in the boxes to the 0 counterpart, which would take us back to the trend model. And indeed, that would be the whole story. We're kind of done. We don't know which one's better. But let's try a different thing. If the model is linear before and after, that should show up. If the model is quadratic in the before and after periods, that should show up. So let's put these tests together, and what we discover is that in the sample period years 1 to 7 and 8 to 14, the t-square variable does not reach any kind of significance. We do not reject that t-square is 0. So we reject the quadratic model in the early period and the later period, and of course we're left with the trend model. This really does say there was a structural break, but we're not done. What these were nested hypotheses. You look at the red part of the equation, and we're testing that goes to 0 under the null hypothesis, and we're left with the trend model. We're testing both models against the trend, and as we saw, they're both valid. The type 3 error here is we're testing the wrong thing. We should be testing one model against the other, and that requires something called non-nested hypothesis testing. Here's the code to do the J test. There is a J test and an F test, and the paper will have all the references so that you can go and take a look at what these are. But here what we want to do is basically in the J test, the first model, we're going to run the quadratic model and we're going to predict the y variable from the quadratic model. And then down at the bottom, last equation, we're going to take the structural break model and we're going to add to it the predictions from the quadratic model. And we're going to ask, does the information coming in from the quadratic model add significantly over and above the structural break model? In other words, is there information we're missing? And that's our hypothesis. And we're going to do the opposite for the other case there in regressions 2 and 3. Then we're going to create a supermodel with all the variables in it, and we're going to test a reduction of this to the structural break model and a reduction of this to the quadratic model, and we're going to compare them. Now the problem with this is it turns out there's 16 different possibilities, and in our case we get pretty lucky, and I'll show you why. So we got 4 different tests. This first test says that the introduction of the structural break predictions to the quadratic model adds significant. Structural break adds over and above the quadratic. Okay, so that rejects the quadratic model. Then we look and we say, does the quadratic model add significant information over and above the structural break model? And the answer is no. So here in the J-test, we've discovered that the structural break model is good, the quadratic model is not, and that's good. I mean, that really is good, but it didn't have to be that way. Non-nested hypothesis testing will not always get you the cool conclusion that you see here. We might find that both are rejected, both are accepted again. In the F-test, we find that testing the structural break coefficients very significant. In other words, D and DT, the parameters on there, add significantly to the supermodel, but the t-square variable, that is the quadratic model, does not add to the structural break. So both through a J-test and an F-test, we got 4 conclusions. Here's all 16, by the way, and we got lucky because they all point to the same thing, and that is that the structural break rejects the quadratic model, but the quadratic model cannot reject the structural break model, and we're at that conclusion. Now we could also do a misspecification test. ProcAutoReg has this, and in this case you can come back, take a look at the code if you will, but we reject the quadratic or fail to reject the quadratic, and we fail to reject the structural break. This puts us right back to where we were. So Ramsey doesn't necessarily help us in this case. And we already covered the use of automatic model selection in ProcReg. So again, this didn't come to any kind of good conclusion as well. But what we did find was that we liked out of this data by inspection that we liked 2 different types of problems. One was a structural break and one was a quadratic. It took 8 regressions and the tests associated with those to complete a testing strategy to convince us that the structural break model was a better representation of the data. Hasty regression only leads 1 test, and it was conclusive, but it said that D didn't matter, and now we find out that D indeed mattered a lot. The quadratic model was tested against the structural break model and non-nested hypothesis. That took 4 different tests to run, and we got the same conclusion throughout all. Ramsey did not help us because both models were acceptable, and automatic processes we see do not lead to the same conclusion. Human critical thinking processes are critical in these cases. So to kind of conclude here really quickly, this paper did not use formal causal calculus. The question essentially is, did the policy change cause the outcome to increase? And you could still argue it's a mathematical process, leads same conclusion. However, economists use theory to shape their understanding of the problem at hand and to develop their strategy. And you see here the strategy was way more than a hasty regression. Judea Pearl, in his book of Why, tells us that data alone can never solve causal problems. And this is really why you want to hire economists into your data science areas. These topics that I'm covering here are not typically taught and represent very valuable acquired skills, proving that applied econometrics and regression analysis is kind of like a puddle in which a novice can wade and the expert drowned. So I hope this presentation has helped you see deeper into that puddle and discover what is important. So how do you know if your data is lying to you? The answer avoids is to avoid hasty work and hasty regression, to be aware of ethical processes and avoid pitfalls in regression practice. So thank you very much.